Ever considered how we first tried to teach machines to think like us?
Hmm.
Long before the dazzling era of neural networks and deep learning, there was this foundational approach.
Right, a really different way of thinking about it.
Exactly. A fascinating intellectual experiment known as the symbolic mindset.
Symbolic mindset, yeah.
Imagine trying to build intelligence not as a fuzzy intuitive brain, but as a perfectly logical, explicit machine.
Like clockwork.
Yeah, where every single piece of knowledge, every concept, every decision followed precise, undeniable rules.
It's like building a mind out of logic blocks, almost.
It really is. So today we're taking a deep dive into this groundbreaking paradigm.
That's-
We've pulled insights from cornerstone texts like artificial intelligence, a modern approach, and mind design,
Seminal works, definitely.
and revisited historical critiques like in perceptrons, and even woven in modern perspectives from A 2041-10 visions for our future.
A good mix of old and new.
Our mission for you is to explore how early AI pioneers really believed intelligence could be modeled just by manipulating symbols and logical rules.
It was a very strong belief back then.
We want to uncover their ambitious methods, their, profound successes, but also their eventual, often surprising limitations.
Absolutely. We'll unpack how these early researchers meticulously encoded, well, pretty much everything.
Like what?
Things like the intricate rules of grammar, complex problem-solving strategies,
Mm-hmm.
and they even made these bold attempts at replicating human common sense within these formal systems.
Common sense. That sounds tricky.
Oh, it was. We'll look at the remarkable successes they achieve, especially in areas like, say, natural language parsing and strategic planning.
Things where rules seem to fit well.
Exactly. They really pushed the boundaries of what machines could do then. But just as crucially, we'll delve into the growing realization
Okay.
that the vast, messy, often ambiguous nature of real-world knowledge was a huge challenge.
One that symbols alone couldn't quite handle.
That's right. Symbols alone struggled to fully capture it all. It's a really critical chapter in AI history.
Mm-hmm.
It reveals how our fundamental understanding of intelligence has just continuously evolved and adapted over time.
So for you, our curious listener, understanding these symbolic roots is, it's so much more than just a history lesson.
Definitely. It's foundational.
It's the bedrock upon which much of today's AI still stands, even if current technologies look dramatically different on the surface.
The echoes are definitely there.
By exploring these origins, you'll gain a far deeper appreciation for both the enduring strengths and the inherent persistent challenges
Yeah.
that continue to shape the entire field of artificial intelligence. It helps us understand why AI is where it is today.
And maybe where it's going next.
The dawn of symbolic AI intelligence as logic and rules.
All right, let's unpack this core idea, the symbolic mindset.
Let's do it.
At its heart, it wasn't trying to mimic the squishy biology of a brain.
No, not the wetware.
Instead, it conceptualized intelligence as the meticulous manipulation of abstract symbols.
Right. According to predefined, explicit logical rules.
Think of it less like a thinking organism and more like an extremely sophisticated, maybe elegant calculator.
Or, like you said, a rigorous theorem prover.
Yeah.
Something very formal.
Yeah. Every piece of information, every concept from something simple like the sky is blue to a complex relationship like cause and effect was represented by a symbol.
Like cocaine.
And intelligent behavior in this view was just the result of painstakingly applying a set of precise rules to these symbols.
It's a very structured, very formal, almost mathematical way of looking at intelligence.
Indeed. And this entire framework is often maybe affectionately referred to as good old-fashioned AI or GOFAI.
GOFAI.
Yeah.
You hear that term a lot. It kind of captures that core belief
Which was?
that intelligent behavior could be achieved by reasoning over these high-level symbolic representations of knowledge.
Yep.
The emphasis was always on the logical structure of thought, the what and how of the reasoning itself.
Right, rather than getting bogged down in the underlying physical stuff.
Exactly. Whether it was silicon or biological neurons, that was secondary. The computation, the logic, was seen as primary.
To give you a mental image, maybe imagine intelligence as a perfectly designed, transparent factory.
Okay, I like that analogy.
Every input has a specific, clear label. Every machine inside performs a predictable, auditable operation.
You can see every step.
And the final output is a direct, traceable consequence of those operations. You could, in theory, follow every single step.
Understand exactly why a decision was made.
Or how a conclusion was reached. This absolute clarity and traceability was, I think, a huge part of its appeal for early researchers.
It offered a seemingly robust path to understanding and building intelligence. It felt controllable.
And that appeal was deeply rooted in a significant philosophical concept, which mind design discusses quite a bit: substrate independence.
Ah, yes, substrate independence. A powerful idea.
What did it propose, essentially?
It proposed that programs and their logical operations were considered entirely independent of their physical realization.
So it didn't matter what they ran on.
Pretty much. It didn't truly matter if the intelligence was running in an electronic machine, a biological brain, or even some hypothetical Cartesian mental substance.
Wow.
This philosophical stance allowed researchers to focus almost exclusively on formal logic and computation.
Decoupling mind from brain, effectively.
Exactly. The profound implication was that the software of intelligence could, in principle, run on any hardware.
Freeing them to focus purely on the logical architecture.
That was the idea.
But the path to symbolic AI wasn't like a straight, uncontested highway, was it?
No, definitely not. In the 1950s and early 60s, there was considerable, almost fervent excitement around alternative models. Specifically perceptrons, which were very early rudimentary forms of neural networks.
Ah, the precursors.
Right. Researchers like Frank Rosenblatt, his works mentioned in These Strange New Minds, even made some rather wild claims about their future capabilities.
Like what sort of claims?
Suggesting they could one day travel to space or perform complex feats well beyond what they actually demonstrated at the time.
Okay, so a bit of over-optimism there.
A fair bit, perhaps. It was a time of immense optimism, but maybe some overreach too.
What's truly fascinating here, though, and a real pivotal moment in AI history, is that this early wave of connectionism faced a formidable intellectual challenge.
You're talking about Minsky and Papert.
Exactly. Marvin Minsky and Seymour Papert with their highly influential 1969 book, Perceptrons.
A landmark critique. Devastating, really.
How so?
They rigorously analyzed the limitations of single-layer perceptrons. They showed, quite definitively, that these early models could only solve relatively simple, linear types of problem.
Things like XOR weren't possible, right?
Precisely. A single-layer perceptron couldn't even learn a simple XOR function, a basic logical operation, let alone recognize complex patterns.
And this critique, as These Strange New Minds also points out,
it significantly killed off enthusiasm for neural networks for more than a decade. A real AI winter for connectionism.
Creating this profound void, this intellectual space.
That symbolic AI was uniquely positioned to fill. It offered a different, seemingly more robust path forward.
It really felt like a fork in the road for AI research.
Absolutely.
So this intellectual shift meant that if even seemingly simple pattern recognition was proving intractable for these early connectionist models, then surely the more complex human abilities like abstract reasoning, problem-solving, language, they must require a more structured, logical, symbolic approach.
That was the inference, yes. It was a decisive pivot away from trying to mimic perception towards trying to rigorously mimic reasoning and logic.
This era then saw the emergence of foundational figures who really championed the symbolic approach.
People like John McCarthy.
Right, a co-author of that seminal 1955 proposal for the Dartmouth Workshop.
The one that formally coined the term artificial intelligence.
Referenced in Supremacy AI. McCarthy's early visions for AI, like automated vehicles.
And she was imagining way back in the 1950s.
Yeah, noted in Human-Compatible Artificial Intelligence. These visions clearly implied systems built on explicit rules and logical deductions.
To navigate and act in the world, he wasn't thinking about training neural nets back then.
No, he was thinking about coding the rules of the road.
It really set the intellectual stage for the symbolic paradigm to take over for a while.
When we talk about symbols here, it's important to clarify we're not just talking about like letters or characters on a screen.
Good point. They're more abstract.
They're abstract tokens, like building blocks representing concepts, objects, properties, relationships.
Anything from block A in a puzzle.
He's on top of.
Or even an abstract goal state like checkmate.
These symbols act as placeholders for pieces of knowledge that the AI can then manipulate.
In a precise, formal way.
The power of this abstract approach is, well, it's wonderfully illustrated by something called typographical number theory, or TNT.
Ah, from Gödel, Escher, Bach. A fascinating example.
Yeah, this formal system, designed to explore the foundations of arithmetic, was described as being of the same strength as the system of Principia Mathematica.
Which was that monumental work by Russell and Whitehead, trying to formalize all of math.
Exactly. TNT showed that within a completely formalized framework, symbols for numbers, rules for axioms, you could, in principle, prove every theorem which you would find in a standard treatise on number theory.
It showcased this immense, almost limitless, deductive power, achievable through purely symbolic manipulation.
For rigorous, formal reasoning, it promised a universe built entirely on logic.
A very appealing promise for many researchers.
No, these symbols aren't static. They're dynamically manipulated by precise, predefined rules.
The engine of the system.
These could be rules of inference and logic, like if A is true and A implies B, then B must be true.
Notice bonus. Classic logic.
Or they could be the grammatical rules of a language, how words combine meaningfully.
Syntax.
Or indeed, the legal moves and strategies in a game like chess.
Right. The intelligence, in this specific view, emerges directly and predictably from the consistent logical application of these rules to the symbols,
creating a clear chain of reasoning.
And this leads us straight to Alan Newell and Herbert Simon.
Key figures.
Absolutely. Their groundbreaking work, Computer Science as Empirical Inquiry, Symbols in Search, featured in Mind Design, firmly established the idea that intelligence itself could be elegantly understood as transactions on a knowledge base.
Transactions on a knowledge base? What does that really mean?
It solidified the perspective that intelligence was essentially a process of computation performed on these symbolic representations.
Where the transactions are those applications of rules we were talking about.
Exactly. It gave the field a very concrete operational computational definition of what an intelligent system was actually doing.
Building blocks of the symbolic paradigm.
Okay, so with these foundational principles of symbols and rules set up, let's look at how symbolic AI actually went about representing all that complex human knowledge.
Right, the practical implementation.
The journey often began with the simplest form, propositional logic.
The building blocks.
As outlined in Artificial Intelligence, a Modern Approach, this system uses basic symbols to represent entire declarative sentences, propositions that are either definitively true or false.
Like it is raining is either true or false.
Exactly. And these are then combined with logical connectives, and or not.
Very fundamental, clear-cut. Black or white, true or false.
Propositional logic, despite seeming simple, is actually surprisingly powerful for certain tasks, isn't it?
It is. It can effectively handle propositions that are known true, known false, or completely unknown. Allows for basic logical deductions.
Okay.
What's more, checking for entailment, seeing if a conclusion logically follows from premises can be done by enumerating models, systematically exploring all possibilities. And impressively, efficient model-checking inference algorithms exist that can often solve large problems quickly.
But it has limits.
Big limits. Its simplicity means it can't represent relationships between objects or quantify over them.
So it could say the sky is blue and the grass is green.
But it couldn't express all birds can fly or John is taller than Mary.
It was powerful, but limited for nuance, like painting with a single blunt brush.
A good way to put it.
So to overcome these obvious limitations and represent a richer, more nuanced world,
they needed something more expressive.
Symbolic AI introduced first-order logic.
A significant leap.
This allowed for predicate symbols like isparentof or israd describing properties or relationships, and constant symbols for specific individuals like John or Apple, and variable symbols like X or Y to represent general entities.
This really opened up the possibilities for knowledge representation. You could express much more complex ideas.
Instead of just, it is raining, you can now express, John is a parent of Mary, or all apples are red.
Exactly. This extension provided a much more expressive language for encoding sophisticated knowledge.
You could define complex rules about the world.
Yes, like a disjunctive logic program could define intricate relationships, allowing for much more sophisticated logical inferences about objects and their properties.
And the meaning of these symbols is tied to a formal interpretation.
Precisely. Constant symbols denote the individual they represent. Predicates specify if a relation holds true.
And you mentioned frame axioms earlier.
Yes. Crucial for reasoning about change. Artificial intelligence and mathematical theory of computation illustrates this well.
How so?
Frame axioms describe how facts about the world fluence persist or change after an action.
Okay, give me an example.
So a complex rule might spell out, if you're holding object X and the object Y isn't broken, and dy is either not X or Ry isn't fragile, then Y won't be broken after you drop X.
Oh, that's specific.
It has to be. It represents knowledge about action effects in a painstakingly symbolic, rule-based way, defining every precondition and postcondition.
With knowledge now meticulously represented like this, many problems could be framed as searching through a state space.
Right. The problem-solving aspect.
Imagine this vast, intricate landscape where every point is a possible configuration of the world.
Like every possible board state in chess.
Exactly. And valleys, or peaks, represent solutions or optimal states.
As described in artificial intelligence, a modern approach.
The AI's task, then, was to intelligently navigate this landscape, find the best path.
And Artificial Intelligence Foundations of Computational Agents explains this well through graph searching.
Sure.
Here, nodes are the state's configurations of blocks, perhaps, and edges are the actions that transition between states moving block A onto block B.
The goal being?
To find a path, a sequence of actions from a start node to a goal node, often aiming for the lowest cost path for efficiency.
Like using a map to plot a journey. Very systematic.
Precisely.
One prominent search technique here was hill climbing.
Hill climbing. Simple but effective, sometimes.
Analogous to literally climbing a hill in the fog, right? You move from where you are to an adjacent spot that seems higher.
Improves your evaluation function. Gets you closer to the goal. It's a greedy approach.
Always taking the immediately best perceived step. But, and this is a crucial drawback.
Yeah, the local maxima problem.
Artificial intelligence. A modern approach warns it can easily get stuck on local maxima and plateau.
You find the top of a small hill and think you've peaked, missing the real mountain nearby.
A classic application of this symbolic search was, of course, game playing.
Chess being the prime example.
For games like tic-tac-toe, or much more complex ones like chess, the different board configurations and possible moves form an enormous game tree.
Huge trees.
Symbolic AI would explore these trees, often to astonishing depths, using strategies like minimax or alpha-beta pruning.
To find optimal moves by evaluating the utility value of the terminal state, predicting the long-term outcome.
Early game-playing machines, like those in Wiener cybernetics text.
They'd start with tentative weightings for different game factors, material, center control, etc.
And then meticulously choose moves that maximize these values.
All operating within a strictly rigid program of predefined rules and heuristics, the blueprint for Deep Blue, essentially.
Beyond just finding a path, the ambition grew to generating coherent plans.
Right, sequences of actions.
Not just individual actions, but entire sequences designed to achieve complex goals in dynamic environments.
Moving beyond simple search to more sophisticated reasoning about the effects of actions.
It wasn't just how do I get there?
No, it was what precise, ordered steps should I take to accomplish X, Y, and Z, accounting for changes.
Mind design emphasizes that rationality here isn't just making a move,
but about optimal design relative to a goal or optimally weighted hierarchy of goals and constraints.
Like in chess, the goal is checkmate, but you have sub-goals.
Win material, control the center, defend the king, each with its own weighting.
The computer's most rational move is derived from its knowledge of the state and its defined goals.
Seeking a provably optimal solution based on the available information, meticulously reasoning through cause and effect.
And to handle environments that weren't entirely predictable, dynamic, uncertain ones.
They developed more advanced frameworks, sequential decision networks, Markov decision processes, MDPs.
Detailed in Artificial Intelligence Foundations of Computational Agents. How do they work?
They explicitly represent states, actions, probabilities of outcomes, and rewards or penalties.
Allowing for formal analysis of optimal long-term policies, even with uncertainty. Baking in foresight.
Exactly. And algorithms like asynchronous value iteration for MDPs or variable elimination for decision networks powered these.
What did they calculate?
The expected utility of an optimal decision. So the system computes the long-term value of actions, weighing all possible future states and rewards.
To select the action that's mathematically optimal for its objectives.
Yes. An explicit, transparent, provable decision-making process, a hallmark of the symbolic paradigm.
Now, one of the most ambitious frontiers for symbolic AI was language.
Human language, the ultimate challenge, perhaps.
Understanding and generating it. The prevailing idea was that language despite its fluidity and ambiguity.
Must ultimately conform to an underlying set of logical rules, like math.
If we could just uncover and formalize these rules of language, computers could understand and speak.
That was the dream. And the work of Noam Chomsky heavily influenced this perspective.
How so? Discussed in These Strange New Minds.
Chomsky famously posited that humans possess innate computational tools, a kind of language acquisition device.
Specifically, evolved to acquire syntax.
This theory aligned beautifully with the symbolic AI approach of teaching language to computers by starting from vocabulary sets, conjugation patterns, and grammatical rules.
A method mentioned in AI 2041. The belief was that language can be broken down into a finite, learnable set of formal rules.
And once mastered, the machine would understand.
The ultimate goal, almost mythical, was often framed by the Turing test.
Ah, the imitation game.
Where the software needs to fool humans into thinking that it, too, is human, purely through conversation.
Seen as the ultimate proof of linguistic intelligence, Symbolic AI believed it could get there via rules.
Did they have early successes?
They certainly showed promise, particularly in natural language parsing.
Yeah, breaking down sentences.
Yeah, identifying grammatical components based on pre-programmed rules. Nouns, verbs, subjects, objects, basic sentence structure understanding.
Right.
Well, it's true that deep learning has superseded these early approaches for many NLP tasks recently.
Right.
The idea of formal grammar and rule-based language processing was absolutely fundamental to early symbolic NLP.
Interesting.
Even some early connectionist work, mentioned in parallel distributed processing, tried using perceptrons to determine connections between features and phone units.
So even they were trying to learn rules from data in a way.
In some sense, yeah. Trying to parse language components, indicating some conceptual overlap at the edges of these seemingly different approaches.
Triumphs and unexpected roadblocks.
Symbolic AI, for all its eventual challenges, definitely had some high-profile triumphs. Moments that really solidified its position for decades.
Oh, absolutely. Big moment.
The most iconic, surely, was IBM's Deep Blue beating Garry Kasparov in chess in '97.
A watershed moment. Captured the world's imagination. Made people think machines could truly think strategically.
Felt like science fiction becoming reality.
Indeed. And as The Singularity is Nearer explains, Deep Blue was a true marvel of symbolic engineering.
Not intuitive learning, then?
No, not at all. It was filled with all the know-how its programmers could gather from human chess experts. Vast libraries of explicit rules.
Opening theory, mid-game strategy, endgame.
All programmed in. Crucially, it used sophisticated search algorithms to navigate that immense game tree.
Plus brute force computation.
Evaluating millions of positions per second, it was a highly specialized chess-playing machine.
An absolute titan within its precisely defined symbolic domain.
It showed that if you could formalize a problem perfectly, symbolic AI could conquer it. But it relied entirely on human-programmed knowledge.
It didn't learn chess from scratch. It was taught chess.
Precisely. A key distinction.
Beyond games, symbolic systems also showed their power in purely formal reasoning.
Right, like that typographical number theory example from Gödel, Escher, Bach.
Capable of proving every theorem in standard number theory.
A profound demonstration of logical consistency and deductive power through symbolic manipulation.
Achieving a kind of perfect, airtight logical truth. If you could formalize a domain, symbolic AI could master it with absolute rigor.
And fascinatingly, even today, in critical applications like autonomous driving, symbolic rules are still vital.
Really? Even with deep learning?
Often working in concert with newer tech. AI 2041 discusses L5 autonomous vehicles where the cost of an error could be extremely high.
Life or death.
Exactly. Solutions often involve augmented roads and cities, with sensors feeding symbolic inputs to rule-based systems.
Like telling the car danger ahead.
Essentially, yes. Think of it like a train on virtual rails, following precise instructions.
It highlights the value of clear, auditable logic in high-stakes situations.
Absolutely. Where human oversight in automated systems is still advocated, as Stuart Russell notes, the ability to trace why a decision was made is paramount for safety.
A strength where symbolic logic still shines.
Definitely.
But despite these impressive successes, this crucial realization began to emerge.
The big roadblock.
That real-world knowledge was too vast and ambiguous for symbols alone to fully capture.
This really became the pivot point, didn't it?
The real world, with all its messiness, subtlety, unspoken context, it just refused to be neatly packaged.
Into discrete symbols and clear, unwavering rules.
Yeah.
It wasn't just complex, it was fundamentally fuzzy.
This challenge was articulated really well by the linguist Leonard Bloomfield.
Ah, yes. Quoted in Mind Design. Very insightful point.
He argued that to achieve scientific accuracy in semantics, meaning in language, you literally need scientifically accurate knowledge of everything in the speaker's world.
An impossible task.
He observed presciently that we have no precise way of defining words like love or hate, because such concepts concern situations that have not been accurately classified.
It highlights the immense difficulty of hand-encoding all the nuanced, experiential, cultural knowledge humans acquire.
How do you formalize empathy, sarcasm, subtle social cues?
It just seemed intractable.
Even those powerful formal systems like TNT for arithmetic,
while theoretically complete,
proved enormously unwieldy as to be, for all practical purposes, useless for everyday mathematical practice. That's from Gödel, Escher, Bach.
The elegance of formalism often came at the cost of practical utility in complex scenarios. It worked, but it was incredibly cumbersome.
This directly contributed to what became known as the common sense conundrum.
A truly thorny problem for symbolic AI.
Ornitzioni and Architects of Intelligence expressed concern about expectations for AI to naturally develop common sense and reasoning.
Explicit rule sets, no matter how vast, just struggled profoundly to capture the implicit, vague, context-dependent nature of human common sense.
Our common sense isn't built on formal definitions, is it?
No, it's built on a lifetime of varied, unstructured experiences. It was this subtle, pervasive, incredible, frustrating gap.
Because common sense isn't just knowing facts.
Right. It's understanding unspoken implications, navigating social situations, predicting behavior, applying knowledge flexibly.
Qualities that proved excruciatingly difficult to distill into explicit rules. It's knowing not to say something blunt at a sensitive moment.
Or understanding the difference between he hit the ball and he hit the wall, steeped in experience, not just grammar.
Consider that classic linguistic ambiguity. Time flies like an arrow. Fruit flies like a banana.
Ah, yes, a great example.
A purely rule-based system without a vast, pre-programmed, highly detailed contextual database would just struggle to resolve the multiple meanings of flies or like.
Formalizing every possible context for every word becomes an intractable task, an infinite regression of rules.
How do you write a rule for every potential joke, every idiom, every double entendre?
But it simply can't.
So the very beauty of formal systems, their clear logical consistency, often broke down spectacularly when faced with the messy, unpredictable real world.
Like, how do you formally define fragile for a robot handling any object?
You'd need to consider material, shape, weight distribution, environment, past impacts.
A million other things. It's not a single rule. It's an emergent understanding from endless experiences.
This fundamental disconnect led directly to the problem of brittleness in symbolic systems.
Rules, however carefully crafted, might fail or contradict one another, especially in complex dynamic scenarios that programmers didn't foresee.
AI 2041 warns about this with L5 autonomous vehicles.
The rules may fail or contradict one another, and crucially, the cost of an error could be extremely high.
This inherent rigidity meant symbolic AI struggled with novel situations or subtle deviations from its programmed world model.
It couldn't generalize beyond its explicit knowledge, great at what it knew, lost when faced with the unknown.
That brittleness was a major practical hurdle for actually using these systems in the real world.
Definitely. If a situation didn't perfectly match a rule or rules conflicted,
the system could crash, produce absurd outputs, or just get stuck.
They lacked the ability to generalize or gracefully handle exceptions, made them unreliable outside controlled environments.
Another critical limitation was the sheer computational complexity.
The processing power required.
Artificial intelligence, a modern approach, notes that NP-hard problems typically have an exponential number of local maxima to get stuck on.
Meaning exhaustive symbolic search could quickly become computationally infeasible, if not impossible.
Like trying to find the highest peak in a vast foggy mountain range by just climbing uphill.
You hit that local maximum problem again, and Minsky and Papert's analysis of perceptrons showed something similar.
What was that?
Their convergence time, how long it took to learn, could increase even faster than exponentially with the size of the problem.
So a slight increase in complexity means the time required just explodes,
making many ambitious projects simply impractical.
This leads to the curse of dimensionality, mentioned in pattern recognition and machine learning.
A well-known issue. As the number of variables or features describing a problem increase, the combinatorial explosion of possible states or rules made the problem intractable for symbolic systems.
The amount of data or knowledge needed grew exponentially.
It quickly overwhelmed even the most powerful computers and programmers trying to model the world.
And perhaps the most crippling practical constraint
The human effort involved,
was the immense knowledge acquisition bottleneck.
the effort for humans to hand code, verify, and maintain these vast symbolic knowledge bases.
Imagine building and keeping consistent a 30 million rule system like PsyCorp Psych.
A project mentioned in these strange new minds trying to codify common sense. A monumental undertaking.
Updating and ensuring consistency for all aspects of real-world common sense.
Proved to be an overwhelming, maybe impossible challenge. It just wasn't scalable from a human effort perspective.
The world changed faster than we could write rules for it.
That sums it up pretty well.
The shifting sands paving the way for new paradigms.
Okay, so the growing recognition of these limitations. Scalability, common sense, ambiguity.
It naturally led researchers to explore radically different avenues.
Approaches focused on learning from vast amounts of data rather than hand-coded rules.
A profound paradigm shift. A different philosophy on how intelligence could emerge.
This shift saw the dramatic, almost meteoric rise of deep learning,
which has superseded these early approaches in areas like NLP, as AI 2041 highlights.
instead of painstakingly encoding grammar rules.
Deep learning models learn to model complex relationships and patterns directly from raw data, finding hidden structures autonomously.
These models are uniquely suitable for computers and scalable with the increasing availability of very large training data sets.
It was a perfect storm. New theory, more data, more computing power.
This paradigm shift is detailed in works like pattern recognition and machine learning and the elements of statistical learning.
Showing how the field moved from discrete logical operations towards continuous mathematical functions.
Progressively representing more abstract concepts, as Yoshua Bengio describes it.
Like moving from a binary switchboard to a continuously variable dimmer, representing much more nuance.
This transition fundamentally marked a move from white box systems
where you could, in theory, inspect every rule,
to increasingly black box systems.
where it's harder to understand exactly why a decision was made, less transparent.
But they demonstrated unprecedented capabilities, right?
Absolutely. Handling the fuzzy, high-dimensional, noisy data of the real world with the flexibility and power, symbolic systems just couldn't match.
It was a trade-off. Interpretability for performance.
Often, yes.
So what were the primary drivers behind this massive shift?
Immense practical advantages and sheer scalability, really.
Data-driven methods offered a compelling way to tackle that vastness and ambiguity that plagued symbolic systems.
Instead of defining every single road sense rule for a self-driving car.
The system could just learn it from data, as AI 2041 notes.
A pragmatist's dream. A way around the knowledge acquisition bottleneck.
And crucially, the explosion of very large training data sets,
which AI 2041 emphasizes, created the ideal environment for these models.
Data became the new knowledge base, in effect.
And deep learning models proved exceptionally good at extracting intricate patterns, hierarchies, subtle correlations from it.
Something previous approaches struggled with, relying on human distillation of knowledge.
It was like suddenly being able to see the forest and the trees, not just hand-drawing each tree.
And the performance breakthroughs were undeniable, often breathtaking.
Deep learning started breaking records on every NLP standard evaluation task.
As proudly proclaimed in AI 2041 and in complex games.
Models like AlphaGo Zero famously learned to master Go without even being given the rules.
A stark contrast to Deep Blue, which relied entirely on expert human knowledge.
AlphaGo Zero, as recounted in The Singularity is Nearer, achieved superhuman performance in a way symbolic systems couldn't.
Demonstrating this new capability to model and operate in complex, unstructured environments.
Learning from experience and self-play, not just explicit, human-coded instruction. A different kind of intelligence. Outro.
So we've taken quite the deep dive into the symbolic mindset.
We really have.
Exploring how AI pioneers envisioned intelligence as manipulating symbols with logical rules.
We saw its elegant power in formal reasoning, its triumphs in chess.
But also understood its inherent fragility, its difficulty with the boundless complexity and ambiguity of the real world.
And that elusive concept of common sense.
It was a powerful yet ultimately limited paradigm that really shaped the early decades of AI.
But while data-driven approaches like deep learning have undoubtedly superseded these early approaches for many tasks, The legacy of symbolic AI is far from obsolete.
How so?
Its core principles, explicit knowledge representation, logical reasoning, structured problem solving, continue to inform hybrid AI systems.
Systems that combine the best of both worlds.
Exactly. That cognitive science distinction between a habit-based system learning from experience, like deep learning, and a goal-based system,
Which searches systematically for the best possible action, like symbolic planning, from these strange new minds.
Right. That suggests both forms of intelligence are likely essential for true artificial general intelligence.
It's increasingly not an either-or question.
But about how these two powerful approaches can synergistically combine.
Reflecting on this incredible journey, from strict rules to adaptive patterns, it leaves us with a final question for you to ponder. If, after decades of exploring both hand-coded symbolic rules and data-driven pattern matching, AI still significantly grapples with true common sense.
Yeah, the conundrum persists.
What does this tell us about the nature of common sense itself?
A deep question.
Is it something that can ever be fully formalized or learned by any computational system? Or is it maybe an emergent property?
Uniquely tied to embodied experience, interaction with the physical world, the very fabric of living and being.
Something for you to think about.